may know, I've been working in AppSec for about 20 years now. I was one of the founders of OWASP and was the global chair of OWASP for the first 10 years. I'm really passionate about this, so I'm really glad that you showed up today. I've heard a couple apocalyptic talks already from, and I know Robert is going to give a talk about InfoSec a little later, so I think that's going to be worth your while. But I'm going to try and give an upbeat talk. I'm pretty optimistic about what we can do in AppSec. I thought, Jim's talk this morning about the history of AppSec was interesting. He framed it up as like, we've accomplished so much. But frankly, if you look at the examples he used, he said we got SSL everywhere and we fixed password encryption or something. Like, really not a lot. I would say in the 20 years I've been doing this, we've fixed almost nothing in AppSec. The OWASP Top 10 is roughly the same as when I wrote the first one in 2002. And it's 20 years later and it's still the same stuff. That's terrifying to me. So I really think we need new ideas. We're still in the Stone Age, and we really need some creative, new, aggressive approaches. I am super excited about what the US government is doing. I can't believe I just said that sentence. But the US government is making application security transparent. They're forcing companies to be open about their SBOMs. They're going to have to create an attestation for their software security practices. That is radical change. When we first created OWASP, we made the mission statement, and I drafted it. And it was, at OWASP, our mission will be to make application security visible so that people can make informed decisions about risk. And that was specifically chosen because when we make application security visible, we can change the market. Market forces can work to encourage application security. Right now, application security is mostly completely hidden. How many of you bank online? Okay, a lot of you, the rest of you are lying. It's true because your data is in those systems anyway. So even if you're not banking online, your data is still there. But how much do you know about the systems that process your finances? Do you know how that code was tested, or who wrote it, or whether it has log4j in it, or if it has known vulnerabilities, or if it was already exploited? You don't know any of that stuff. That's a little terrifying. And you don't know that for everything that's important in your life. It's all controlled by software. Your healthcare, your finances, your government, your elections, your military defense, your social life, it's all controlled by software. And you don't know anything about it. And that's ridiculous. I believe it's actually a fundamental human right. We have the right to know about how the software that we trust with everything important in our lives is secured. And we have to make that change. And it's, Jim's last point in his talk was correct. It is about you. The future of AppSec is about you. But, okay, so that's a little rant. Let's move on to the topic of today, which is runtime protection. I'm going to talk to you about how you can use it and what it's really all about. So first off, I got some cool data from Forrester. Look at the plans to adopt for organizations that Forrester found out. Plans to adopt runtime protection are incredible. It's like 15 to 20% companies are planning to adopt, and more than half, 60, 70% are adopting runtime protection. It's really a fundamental technology to application security. So I'm super excited about it. By the way, that first slide, that was what is your pro tip. It's called your hook, right? It's exciting. A lot of people are using this. It's also in a lot of government standards. It's in NIST 853. It's in the PCI SSF, which is sort of replaced the PCI DSS. So runtime protection is here. It's being used widely in a lot of companies. We'll talk a little bit about that. But some of you may not know exactly what runtime protection is or how it works. So I'm going to zoom way out here, start over from the beginning, and explain why this is important and what it's all about. When you think about AppSec, there's two ways that you can actually improve the security of software. The first is you can try to coerce people to do what you want, right? You got to coerce developers to make different choices about how they write code, right? And we have a lot of stuff that we do to try to coerce them. We have policy and requirements and threat modeling and vulnerability reports and what else we got here? We got training and dashboards and public criticism, SBOMs. All of that is designed to get developers to make the right choices, right? We're trying to coerce them to make the right choices, and it doesn't work very well. The average application has roughly 30 vulnerabilities. This is a very difficult path. We had a 40% fail rate on fixes. When I ran a consulting company for a long time. We used to give development specific directions on what they needed to do to fix their code. And 40% of the time, they did something different than what we told them. This is a really hard problem to get folks to do what you want. The other path we have to make applications more secure is we can put a perimeter around it. That's tough, especially these days. You're trying to surround an exploding attack surface that's probably in multi-clouds, multi-technologies, serverless, APIs, web apps, mobile, and you're trying to detect whether traffic is good or bad at the perimeter. All you can see is the HTTP request or whatever other kind of request it is. It's almost impossible to tell the difference between good and bad, and you have no idea anything about what that traffic is going to. So this is a really difficult problem and ends up breaking applications and leading to endless tuning, which actually ends up being another people problem. So these approaches they're not fantastic. And I was thinking maybe there's another way. Like, what about ASLR and DEP? You guys know what those are? We're not going to dive deep into this. These are technologies to help prevent buffer overflows, address space randomization, and data execution prevention. And what's cool about them is they're not either of those first two techniques, right? You can use these techniques to add protection to existing software. You don't need to change the code. You don't need to do anything. And it makes previously vulnerable code safe. Now, they're not perfect, but it's a really interesting technology. So you think to yourself, like, what could we do that's like that for application security? A third way. That's what runtime protection is all about. So first I need to teach you, what runtime protection is. There's a lot of misinformation out there. Some people are trying to describe their WAF as being RASP. A little complicated, but I'm going to tell you how I think about it. So runtime protection automatically adds targeted security defenses to an existing application. It introduces two things: lightweight trust boundaries in the application code itself, and some sensors to gather information from the application. We'll talk about how those work in a second. But the upshot is that we can eliminate human error. We can fix vulnerabilities this way. Let's walk through how this works. So imagine you've got your code sitting on the file system down at the bottom there, and you've got, as the code loads, there's a bunch of modules in there that are dangerous to use, like the expression evaluation engine, or the SQL driver, or runtime.exec. All these are they're powerful modules, and if developers don't use them right, that's when vulnerabilities happen. Okay? So what runtime protection does is first you add this runtime protection module. It's like a library in most applications. It actually works a lot like APM tools like New Relic or AppDynamics. Just add it to the application server, and then as that application loads, we can introduce these trust boundaries around these dangerous capabilities to protect them from being exploited. So we change those dangerous capabilities, now they're protected capabilities. And the cool thing is these things are really simple. I'll show you in just a second exactly how these work. Now, just to make sure we're clear on the terminology, you may have heard of interactive application security testing, IaaS, and runtime protection or runtime application self-protection, which is RASP or runtime protection. They're very similar. In fact, they're the same runtime security module. You just use one in development to detect vulnerabilities, that's IAST, and you use runtime protection in production to prevent vulnerabilities from being exploited. Okay? So one technology, two different use cases, essentially. Today we're talking about runtime protection. We're talking about production and what happens there. Now, you may be angry stick guy here, going, this sounds dangerous. Wrong. This is really well-proven stuff. We've been instrumenting code for 20 years. It's used in almost every web app framework that's out there. This is a powerful technique for getting your code the way you want it. Like I said, it works exactly like APM tools. And the way I think about it, it's a way of building software. Instead of programming everything in source code and building it and delivering it, instead, there's another path for code to come into the application. It's essentially aspect-oriented programming, if you're familiar with that, where we're weaving in certain code at runtime because it's hard to get the developers to do it in all the right places reliably. Everybody with me so far? Let's take a look at an example of how this. I'm going to look at 5 examples actually really quick. These are different kinds of trust boundaries that we're going to introduce into an application. And my point in showing you these 5 is so that you can understand how simple and powerful this technique is. So let's look at the first one. It's an untrusted data boundary. And all this means is we want to prevent untrusted data from reaching certain modules. Because if it did, that would be a problem. So I'll use an unsafe deserialization example. You never want to deserialize untrusted data because what can happen? Yeah, it's a bomb exploding. See, that's usually bad. So in this case, you can see a serialized object comes in, flows through the web app, goes to the deserialization engine, like in Java, it goes to read object. And as part of deserializing that object, you're going to call the constructors on a bunch of different objects. That's called a gadget chain, and the attacker can abuse it to get their code to run. They can completely take over your application. And this is one of the main vectors used in like log4shell and some other things. So we can do this. We can weave in an untrusted data barrier into the deserialization engine so that it just does a simple check. And here's what it looks like in the code. Oh, and when we do this, that'll prevent this attack chain from happening. So here's what it looks like in the code. Before, you can see some code from the Java read object method. And this is the code that we weave in using runtime protection. It's a simple check. It says, if is data from untrusted source, and then this is the input stream, then we throw a runtime protection and kick it out. This is a super high performance check. It's almost immeasurably fast. And it's perfect. It prevents any untrusted data from being deserialized and prevents this whole class of attacks from happening. Everybody with me so far? Yeah. Excellent. So you won't see this in the source code, right? This instrumentation happens as the application starts up. As the binary code's being loaded, we're going to weave in. This is a static method call. It has no side effects. So it's a very safe thing to add into the code of your application. And then it just runs as though the developer programmed this into their application normally. It just runs as part of the application. Let's do another one. This one's called a semantic integrity boundary. And what this means is, we'll use SQL injection as an example, but we're basically just verifying that untrusted data didn't change the meaning of a command or a query. So I'll do SQL injection, but there's there's a lot of different places where injection could happen: command injection, LDAP injection, expression language injection, and so on. In this case, we'll do SQL injection, and you can see the attacker's data flows into the query. You guys have all seen this. Modified the meaning of the query. Well, how do we protect against that? Here's what we do. We add a semantic integrity checker for SQL here. And all it does is it looks at that query and it recognizes, hey, that untrusted data, that or 1 equals 1 piece, changed the semantics of the query. We can detect that easily. It used to be just a value. And now we know that it's an actual, it's another whole sub-expression. That's easy to detect, very reliable, and it should never happen. No attacker should ever change the meaning of your query. So this is a very accurate way of detecting SQL injection attacks and preventing them from exploiting the application. So the code looks just the same as we looked at before. Now we've got another check called, is query structure modified? And we know in that query is some untrusted data. We'll check to see if it modified the meaning of the query, and then we can intervene. Prevent SQL injection. Now this would be a cool check if your developers were doing it in their code. Problem is, it's really hard to get them to do all the right things. How many best practices for secure coding do you think there are? A lot. He's spreading his arms like a condor. Yeah, I mean, hundreds for every language, and then hundreds more for every framework in every language. It's a colossal amount of things that developers have to learn. Yeah.
So the application developers, do they sometimes blame the RP for injecting code in there and just kind of not wanting to debug it themselves and just hope their favor?
It really doesn't happen because these tests are so simple and so correct that there's no blame that nothing broke. We deploy runtime protection on thousands and thousands of applications in large companies, and they just turn it on and it starts working. We have very little feedback on breaking applications. The one that I can remember is when the application actually sent full queries from the client to the server and was executing them. And runtime protection said, hey, you can't execute those queries. But it was really SQL injection by design. So runtime protection was doing the right thing because it was super insecure. But it doesn't break applications, and that's the whole point. It's incredibly safe to do this. And I just want, what you should compare against is not whether it's perfect, but whether it's safer than not doing it. Because these vulnerabilities break applications if somebody finds them, or they don't even have to find them. Sometimes you ever go to a web page and just typed in, some special characters and it blows up? That's a breaking app. Okay, so that's a good example. Let me do another example. This is an unsafe function boundary. So some functions are just dangerous. In this case, let's look at an example where the data doesn't come from an untrusted source. It comes from a trusted source, an internal MQ. Okay? Maybe the attacker figures out a way through some other API or some other interface somewhere to get untrusted data into your MQ, but we don't know it's untrusted, right? Generally, we trust things that come from our internal systems. So in this case, we can't use an untrusted data boundary. Right? We could say, we don't want any untrusted data into our expression language engine. But in this case, that's not going to work because this is trusted data. So we need another check. So we can put an unsafe function boundary in this app that prevents dangerous calls from being invoked from within a dangerous module. So what we don't want is we don't want the expression language engine calling runtime.exec. Can anybody think of an example when you'd want an expression to invoke runtime.exec? Expressions are for pulling data out of beans and putting them in web pages. They're not for running code. And so it's essentially a sandbox. We can limit what the expression language engine can do and prevent it from doing harmful things like calling runtime.exec and creating sockets and things like that. So that's 3 boundaries, all very simple that we can put in place. Let's look at a couple more quickly. Anybody familiar with XXE? I think it's one of the OWASP Top 10. In this case, the attacker sends an untrusted XML file. And you can see in it there's a malicious doc type. That passes through the application in an XML parser, which interprets that doc type, in this case, accessing the password file and sending it back to the attacker through the application's output. It's a dangerous attack. You can use this to scan internal networks and a bunch of other stuff, anything you can do through a URL. We can stop this attack with something called a defense enablement boundary. We can add capability to turn off doc type processing in this application. So whenever we see an XML parser, we can just configure it to have doc type processing turned off. Doesn't hurt anything. Most folks don't need doc types in input that they're taking from users, so we can disable that with introducing 1 or 2 lines of code into this application. And that'll solve XXE. So look, we've just eliminated a bunch of different kinds of injection. We eliminated back-end connection, like expression language injection. We've eliminated, what else did we do? The first one was unsafe deserialization, a bunch of different classes of vulnerabilities. Just take them off the table because we've got a way of introducing code to prevent them into the application. I'll do one last one. This is banned behavior, and we need a boundary to stop, oops, we need a boundary that will stop things that we never want to happen in the application. We looked at a whole bunch of different Java attacks, and many of them rely on the attacker sending some input that tells the class loader to load some classes into memory. So this is an example where you can see, this is what Spring for Shell used. You can see in this case, this attack accesses class.module.getClassLoader and then forces it to load some extra classes into memory. All these techniques require using reflection to access the class loader. And no developers ever need to use reflection to access the class loader. We actually put this rule in kind of a beta test and pushed it out to hundreds of thousands of applications out there. And none of them use reflection to access the class loader. Anybody know why? Because developers can access the class loader super easily. Every class has access to the class loader that loaded it in it. So you don't need to use reflection to access the class loader. You can just say get class, and you've got the class loader. So using this technique, we can just stop it. We can say, hey, you can't use reflection to access the class loader anymore, ever. And we eliminate a whole bunch of attacks. Anything in Java that tries to leverage this, and it's a bunch of different things, like even some deserialization attacks use this, like if you're deserializing XML, use a class loader, and you use it to get the runtime class, and then you call get runtime on it, and you execute. We can stop all of that with one simple protection. So see what we're doing here? We're fundamentally eliminating whole classes of vulnerabilities. Anybody got any questions on any of that? Okay. Runtime protection also includes a bunch of observability stuff. Since we're already instrumenting the application anyway, there's a ton of interesting data we can gather out of a running application that's useful for a bunch of different AppSec purposes. We can gather information about what's upstream from the application by looking at headers and things. We can look at all the routes, the endpoints of an application to determine the attack surface, detailed attack surface, exactly what kind of requests are used, exactly what parameters are used within each route. We can figure out what the architecture looks like. We can even see the access control matrix. All we have to do is check exactly where access control checks are done and what role is being asked for. And we can generate an access control matrix for the app. We can see all the encryption that's used, what algorithms, where it's being used. We can see all the libraries, and not just see that there's a library there, but we can actually see if it's loaded into memory and if code in it actually runs. And then I think all the outbound connection details on the back end. So imagine you could just add runtime protection to your application, use it for a little while, and then have an application software security model generated that just tells you, here's all this stuff about this application. You can use that upstream. You can use that when you want to do library security. You can do it to empower your pen testers. Imagine if you gave a pen tester a complete list of the attack surface with each route, exactly what parameters are used on each route, and exactly what back-end connections are invoked from each route. It's super powerful. This is a great set of information to do threat modeling from. You can identify vulnerabilities in production this way. There are a bunch of different things that you can do with this. But so runtime protection is a little broader than just preventing vulnerabilities from being exploited. And it's easy to deploy at scale. Well, we've done this a bunch of times on thousands of applications at once. The way I think about it, runtime protection is really a zero trust approach to application security. Instead of trying to create one big perimeter, instead we're blowing up the perimeter and each application server protects itself. Each app has defenses built into it. Doesn't matter where these applications run. You could take them, you can put them in a container, move them to the cloud, do whatever you want. The protection goes with the application. So very zero trust philosophy here. It's fully distributed. So all this protection gets done in place by all these applications. It's not like we've got a gateway. It's not like we're calling out to some other service to do the security for us. We're doing it in a very distributed way. So it's super high performance. And you can deploy it automatically with Kubernetes operator. You can build it into your gold server. You can push it out however you deploy code. You can add runtime protection to that and push it out automatically wherever it needs to go. Okay, so that's how you get it out there. And then, this is probably the first thing you'll see is attack data. You're going to see your applications are getting attacked about 5,000 times every month, each app. You probably don't have visibility into this. If you're looking at WAF data, it's so noisy because everything the WAF sees that looks like an attack, it has to treat it as though it is an attack and block it. Runtime protection doesn't. Runtime protection sees tons of attacks that never connect with their corresponding vulnerability. It's actually 99% of attacks never connect with their intended vulnerability. SQL injection attacks that don't connect with a SQL query. File path traversal attacks that don't connect with file interface. All kinds of attacks like that. So you can ignore most of that. It's nice to know that it's happening, but you can ignore most of that because what matters is the ones that are reaching their corresponding vulnerability. So you can help out your operations team by not flooding them with zillions of attacks every month. If it's 1% of 5,000 attacks, that's only 50 things that they've got to really deal with every month. Nothing. Okay, so we're at the halfway point here, a little over actually. So hopefully nobody thinks that runtime protection is just a WAF. It doesn't work based on network traffic. It's not at the perimeter. It protects from within the application, and it's far more accurate and even more performant than doing this at the perimeter. There's no extra hop, so this is much more efficient. The rest of this talk I want to spend on okay, so that's cool technology, but how does this help my AppSec program? Because that's really what matters, right? Is how is this going to change the situation on the ground? I wanted to show one case study. This was with a large Fortune 75 insurance company that rolled out runtime protection across a lot of applications. Through their testing, they knew they had 1,560 vulnerabilities in the apps that were protected. They did the analysis and found that runtime protection addressed 95% of them. So only 76 of those vulnerabilities were left in the application. And so, if you cut this down to just 76 vulnerabilities, that's a massive improvement in security. And their reaction was, okay, well, we're doing this. They mandated runtime protection for all of their public-facing web applications. That's a really efficient way of protecting your whole portfolio. And it works on not just custom code vulnerabilities, but also tons of CVEs. So look, we're protecting the whole application, not just your custom code, not just open source libraries, but also the app server and the runtime platform and how all those pieces fit together. Runtime protection protects the whole stack, the whole workload. Okay, so I want to take a few minutes and just talk about a few initiatives and that people are doing and how runtime protection helps there. So just by show of hands, who's trying to tackle open source security in their organization? Anybody? Yeah. Good couple of people. Who wants to shift left? Yeah, some other people. Okay. Who wants to do API security? It's all the same people. And I want to secure my legacy code. Anybody got legacy apps out there? Okay, right. These are problems that almost everybody's working on. So let's look at how runtime protection can help. The first one, I want to tackle open source. So the traditional approach, what do? Well, you got to start scanning stuff, right? You got to get an SCA tool. You got to start scanning repos and servers and containers, and scan your serverless. You got to investigate a bunch of alerts to see if those libraries are actually used in the applications that have been flagged. Then you got to update the code, rebuild, retest, redeploy. It's a lot of work. And you got to repeat that every time either the app changes or there's a new CVE out. How often do new CVEs come out? Yeah. So conservatively, I think, if you include the tool cost and the labor cost, and generally, I think in AppSec it's like 20% tool cost and 80% labor. If you add that up, I think a very conservative estimate is like per app, you're spending $20K on open source security. Is that reasonable? Too high? Too low? Some low? I don't know. I think you can put your own numbers in here. I don't care. You should actually add it up, by the way, to know what it's costing per app per year. It's a really useful metric for your AppSec program. But look at what happens with runtime protection. One-time install, push it out to all your applications. You can push out to a whole Kubernetes cluster all in one shot. And you get automatic SCA happening on all your applications continuously. So it'll find all the libraries, report them all centrally, generate SBOMs for all your applications as they exist in production. So full SBOMs, not like the partial SBOM you get if you scan a code repo. Full SBOM, libraries from the platform and the app server and everything. You can focus on which libraries actually load and run. So you can eliminate, we found 62% of libraries never load into memory. No code in them ever runs. They're like dependencies of dependencies where you're not using that feature in the top level. So tons of libraries just along for the ride. Anybody heard that statistic that says 80% of applications are open source libraries? Horse crap. If you look at the code that runs, they're 2/3 custom code and 1/3 open source. And we measure this across a zillion apps. And with this, you not only find out where all the problems are, but you're actually protecting against both known and unknown vulnerabilities in those libraries. So runtime protection can't protect against all library vulnerabilities, but for ones that are in known classes of application security, like path traversal and SQL injection and expression language injection and unsafe deserialization, all the Spring for shells and log for shells and Atlassian vulnerabilities, runtime protection has protected against all of those. No fire drills. You're safe when a new CVE comes out, and you can go update the libraries at your leisure. This is a very different way of managing open source security that I think has a lot of value. And if you look at the total cost, I think you're going to spend way, way less on open source security this way because you focus on what matters. Let's talk about API security. So the traditional route, you get developers to install, configure, and tune SAST, DAST, or SCA. Maybe those are part of some API security tool. Typically, those are like DAST inside those things. And then you're going to get a bunch of results. You got to get developers to triage those things, eliminate false positives, make changes to the code, retest, redeploy. And ultimately, you're going to end up with a big backlog of vulnerabilities that doesn't get fixed. I've seen it over and over again. I think this is $50K a year, not for every API, but for like a collection of APIs that's managed by one team. I think of that as kind of a good way of thinking about the cost. And runtime protection, totally different. Works exactly the same as I've described here. You install it one time, you'll find a bunch of vulnerabilities in both custom code and libraries. Development teams will also get threat intelligence, feedback on what's going on in production so they can focus on the vulnerabilities that attackers are actually targeting. And you can get a bunch of information about the threat model and so on. Cost is much less for doing API security with runtime protection than with a traditional AppSec API security product. Same kind of value with your legacy apps. one thing about legacy applications is it's difficult to sort of shift left because there is no left. It's not under active development, right? So I don't know, what percentage of your applications are legacy apps in your old organization?
I would say 30%.
30% legacy and 70% new development? Oh, wow. It's usually kind of backwards from that, but it doesn't matter. That's you. So whatever percentage of your portfolio is, legacy applications, you got to think about a little different process for securing them. Adding RASP to them is a really fast way of getting great coverage over all those applications. Imagine if you could eliminate all the different injections, most of the OWASP Top 10, path traversal, XXC, unsafe deserialization, expression language, and so on, all in one shot. You can do that for very low amount of money with runtime protection. And doing it the old way is really hard. You're going to scan all those applications. You're going to get a zillion vulnerability reports. You're going to have a massive backlog. Somebody's going to have to triage them all. There's going to be, what percentage false positives? Big. And so I think, $50K a year per, I'm on the API security side. Did I? All right, I didn't switch, sorry. 20K a year, I think is pretty low for those applications. I made this lower because they are legacy applications, and if they're not changing a lot, then once you go through this process a few times, you'll find less and less. But still, a decent amount of cost. You can do this very quickly with runtime protection. And when I add this up, you're going to spend a lot. I average these things out because there's some overlap between these classes. So you want to tackle open source. Open source is part of shifting left and part of API security and part of legacy code. So I did a little math on this. But I think, $36K a year per app is probably pretty low for most organizations that want to do traditional AppSec. You can get better results with runtime protection for much less. Better security, better protection. And I'm not saying don't go fix those vulnerabilities, but you can do it in a much more efficient way than if you had to go through the traditional approach to this. If you want to try runtime protection, one way to do it is to grab a copy of Jot. This is an open source project I created that allows people to experiment with instrumentation. Instrumentation is actually a little tricky to get started in. It's a weird kind of programming, right? You're writing code that modifies other code or inserts instructions into other code. So I made it really easy. You can define I call it a Jot, in YAML. And this one is to prevent expression language injection. It's really simple. You say, hey, in these methods, in the value expression.getValue method, we want to prevent calls to process builder and socket creation. So this is the kind of protection I talked about earlier. If we see that pattern match, we're going to throw an exception that says, hey, attempts to perform expression language injection. It's super powerful. You can add sensors for whatever you want. Whatever you want to measure out of a running Java application, you can do it with Jot in just a few lines of YAML. You can create some really powerful protections. Everyone should probably be running this rule on their applications to prevent expression language injection, especially if you're using Spring, because they've had sort of a series of these attacks. But you can find that. It's fun to play around with. But I think the power of runtime protection is when you start thinking about a collection of these rules that can protect you from all of the OWASP kinds of vulnerabilities. So at the end of the day, who do you trust to get the code right? And this is my wrap up. This is Matlock summarizing the end of the case. So we went through all that stuff. You can choose to try to coerce people into getting the code correct with a whole bunch of tools and output. It's really hard. We've been trying for 20 years and it doesn't work very well. Or you can try to put a perimeter around your applications and filter out the bad traffic from getting in, but we've been trying for 20 years and it doesn't work very well and it's super noisy. Or you can have an army of robots continuously ensuring that your code has all the best possible defenses at exactly the right point in the code to make a decision about whether something is an attack or not. those are the choices. And I think this last one is far more efficient and far more effective on a number of dimensions. So with that, I'll stop. I would love to take your questions. Boyd. Oh, thank you. Turn that on. Here's a question over here, Boyd.
I'm failing the intelligence test of turning this on.
So do you see more traditional tools like SCA and whatnot used together with runtime protection, or do you see the runtime protection eventually replacing the traditional tools?
Well, it's a good question. I mean, we have ASLR and DEP, but people are still using tools to detect and prevent buffer overflows. I think that's smart. I think the best strategy here is a little bit of belt and suspenders. Sure, work on the code, try to get it right, but the first thing you should do is get runtime protection in place, right? That's like locking the front door. Then you can go work on all the details. But I think for most organizations, it's the right first move. Like if I was a CISO coming into a new organization and I'd had no confidence that my software was secure, I would put runtime protection on all of them and then go back and say, hey, let's start cleaning up the code and make sure our new development is secure, our libraries are getting straight. But it's really fast to push out runtime protection. We have one company that pushed it out to 6,000 applications in a matter of a few months. So you can scale really fast and get massive improvements in your AppSec program. Yeah.
Can WAF and runtime protection both can coexist?
Yeah, absolutely. A lot of people do that. They leave a cloud WAF in place. They don't configure it. They just let it catch the low-hanging fruit, people like to call it. I don't know why. It's not a good analogy, but they use that to filter out some basic stuff, DOS attacks and so on, and then they've got RASP to do the real protection against the interesting attacks.
Okay, thank you.
Yeah, great question.
Yeah, so this is it's a thought more than a question maybe, because I agree with everything. I think runtime protection is probably the thing to have. But they did some studies on the effects of self-driving cars, how that affects our psychic. And they sort of came to the conclusion that we're going to just become much more careless when we're out walking. We're going to walk in front of a car because we know it stops. Is there a risk that runtime protection actually makes code worse?
Yeah, that's a good question. That's something called, in economics, that's something called a Nash equilibrium. And it means that, there's all kinds of those, people drive faster when they have seatbelts, and they're more reckless on bikes when they have helmets, and all kinds of things like that. I guess, culture-wise, I don't think I would try to let people think that runtime protection makes it okay. I think, you still want to build a culture of security, but I think, changing the focus from dealing with these individual vulnerabilities to focusing on more difficult strategic issues like threat modeling, access control, authentication, encryption strategy. Those are things that tools will never solve. But we are wasting 100% of our security expertise brain power on chasing cross-site scripting. It's nuts. And we need to focus on those more strategic issues because really those are the things that'll really kill you. Yes, Boyd.
Can you go back to your last slide?
Yep.
So some really tall guy a while ago informed me about defense in depth. I'm not going to name which tall guy. There's a few in here. And it seems to me that you're making a defense in depth argument. Put the WAF or put the RASP out in front, and then you've
The WAF out in front?
I'm sorry, the RASP out in front. Put the
RASP doesn't
out.
go out in front. RASP goes in the app.
Well, I'm sorry. I'm thinking about layers of security.
Oh, yeah. So
RASP
the first thing you do is RASP.
To protect all of those humans and all their human time against all of the noise, the false positives, so they can focus on what matters. Then the perimeter comes next to filter out whatever the perimeter can filter. So now your humans are working on a much smaller set of far more important things. Is that fundamentally what you're trying to tell us?
I think that's fair, I often say in AppSec, we need to prioritize for learning. And I think that's a corollary of this, is like you want to focus your people on the interesting, hard problems that automation can't solve. Right now in AppSec, we have a tendency to use every tool for every job. Like if you're building a house, you would hammer the nails with the hammer, but you'd also hammer them in with the saw and the drill and a bunch of other stuff. And it doesn't make any sense. We need to use our automation wisely, and that means using the right tool for the job and sort of protecting humans from sort of the noise overload. So the question is like, hey, what happens when APM tools offer runtime protection? I mean, it's not a terrible idea. It's not necessary, because APM tools and runtime protection can run side by side. We run side by side with, AppDynamics and New Relic and Datadog and all those. Personally, I think doing AppSec right requires a whole company that's focused on AppSec. There's a lot of expertise that went into creating the rules and getting them right and not breaking apps. And, I think that's really valuable. I suspect that the APM versions won't be as sophisticated, but I'm glad they're doing it because it's the right thing. I usually say every complex thing in the world is instrumented, right? Your car, airplanes, nuclear power plants, space shuttle, industrial factories, they're all instrumented like crazy. Modern industrial factory is instrumented for smoke and heat and fire and noise and vibration and everything. They know when a problem is going to happen way before it actually happens. Like if you've got a bearing loose in a machine, they'll detect it from the sound or the vibration. And then they can fix it and not go down. That's what this is all about. Software is arguably the most complex thing man has ever created. And it's barely instrumented at all. Log files suck. We need to instrument for security. Thank you. We need to instrument every piece of software for security. And I'm not kidding about every piece of software. I mean in your dishwasher and your toaster and your plane and your car. Instrumentation lets you see what's going on inside. Otherwise, it's just a black box and it's going to blow up when it blows up. It shouldn't be that way. I think that's a fair point. I mean, there's products, but there aren't any, the market hasn't evolved to the point where there's like open standards for runtime protection, but there will be. I'm 100% convinced that, in the next few years that software is going to be instrumented. It has to be. It can't survive the way it is.
Yeah, I'm just wanted to add to his point about like making us lazier, because I'm a software engineer, so I'm kind of thinking about it from that perspective of like,
yeah,
we said the same thing whenever like third generation languages came out, or even second generation languages. We're like, yeah, we're gonna get lazy with memory management, and so thinking about that, like, yeah, we're probably gonna get lazy with like these really like high impact security vulnerabilities. But it's just because we don't have to worry about them anymore. Overall, that's a better thing. We became more productive.
I think it's a controversial opinion, but I'm going to say that might not be bad.
Yeah, exactly.
Like,
that's what I'm saying.
If we make these vulnerabilities impossible, like when we say we're turning off doc type processing in all XML parsers, that pretty much makes XXE impossible. And so should we be wasting valuable developer and security time on dealing with XXE, or should we just say, hey, let's focus on what's really a problem?
Yeah, agreed. And so I guess taking a really like extremely high level view about this whole discussion, it makes me think at some point we're just going to have runtimes that are instrumented already for this sort of things. And that kind of seems like that's like
what you should have in your organization. All your platforms should be pre-instrumented, so you can, whenever you deploy a new application, it's automatically protected.
Yeah, this seems like the first step in a new generation of runtimes, essentially, that are instrumented, and that's just the way it is in the future.
Yeah, I absolutely think that's what's going to happen.
What do you think about runtime protection in like a serverless or like a unikernel type scenario?
Yeah, great question. So many of those environments don't support instrumentation yet, because when you're deploying serverless, you deploy a little piece of code and it runs on a platform that's been all set up for you. But the future is that there's exactly what he said, is there's instrumentation built into that platform so that it is there automatically for you. There's just not a great way to do that as a third party yet, but that's going to happen. It's already happening. There's things like layers in AWS and so on. So it's going to happen. You need it for APM purposes anyway. And so runtime protection is really just riding the coattails of observability anyway. So, yeah. Okay. Thank you very much, everybody. Appreciate it.